this session is going to have two components. So we are going to show SANSA's space weather and Earth observation programs working together to safeguard critical infrastructure. So the space weather component will focus on the October 2024 storm, which impacted GNSS applications, featuring expert analysis, real-world user experiences, and insights into forecasting tools that protect aviation, power grids, and navigation networks. And the second component is the Earth observation component, highlighting the development of South African Earth observation system of systems and the use of autonomous agents to monitor agriculture and natural resources, demonstrating the value of integrated space-based and Earth observation solutions for national resilience. So I'm going to call on the stage the speakers in this order. So the first speaker will be Ms. Witumelo Makobe, a space weather forecaster. And the second speaker is Mr. Greg Ritz, the manager of Air Race X, Patrick Davidson. The third speaker is Ms. Nkosinati Masango, a space weather forecaster, SANSA Space Science. And the fourth speaker will be Colonel Mark Wilson from the South African Air Force. And then we'll have Mr. Muloko Sibake, the Chief Data System Manager, SANSA Earth Observation. The last speaker is Dr. Cecilia Masimula, Principal Scientist, SANSA Earth Observation. So we will start with Ms. Witumelo Makobe, who's going to talk about the impact of an extreme space weather storm on GNSS application in South Africa. GNSS is Global Navigation Satellite Systems. Over to you.
Good afternoon, colleagues. My name is Witumelo Makobe, as Dr. Mpo has mentioned, and I am a space weather forecaster at the South African National Space Agency, Space Weather Center. So today I will be talking about the impact of an extreme space weather storm on global navigation satellite system application in South Africa. So basically, what space weather is how conditions on the sun and in space can impact our technological systems that are on the ground and also that are airborne. So most of these technological systems, we rely on them for our daily activities. The Chief of Staff mentioned this morning that we are the users and also the protectors of these technological systems. So within space weather, we use satellite imagery to monitor the sun, and then through space weather monitoring and predictions, we are able to protect these critical infrastructure from space weather effects. So we basically use satellite imagery and also use ground-based systems to basically be able to measure the impact of those eruptions from the sun. We also use what we call numerical weather predictions to predict the arrival time or the impact time of these eruptions that occur on the sun. Also, As I've mentioned, these products that we use, or so to say, space weather forecasting, it helps to inform decision-making, and also it helps the industries that are affected to take precautionary measures and implement mitigation that is necessary. So some of the products that we use, that we do here at the Space Center, includes the Space Weather Bulletin, alerts and warnings for high-frequency communication, and also for the global navigation system. We also do high-frequency predictions, research, and through the research, we are able to use whatever products that are used to forecast space weather. Okay, so as I've mentioned, I will be basically looking into the impact of space weather on the global navigation applications. From the imagery, we can see that quite a number of infrastructure rely on global navigation system, including your banking operations, transportation systems. There's been a case in 2015 in Sweden where the radar data was not being correctly read by the air traffic control. So basically that led to a 90-minute outage, and it meant that the aircraft had to stay on the air for about 90 minutes because there was no communication between the radar system and also air traffic control. So space weather can cause signal delay, positioning errors, and geolocation errors, and reflection or distortion of signals from GNSS. So this geomagnetic storm that occurred between the 6th and the 12th of October is very important, especially for South Africa, because in most instances there are there's basically limited examples of space weather effect in South Africa, especially in the mid-latitude. So most of these impacts that are reported are in the higher latitudes. So this geomagnetic storm reached a KP of 9, which is what we call an extreme geomagnetic storm. And this was due to some eruptions from the sun that we call coronal mass ejections, and also solar flares. Some of the impacts that were observed globally from this storm include this storm may have resulted in the possible re-entry of a Starlink satellite. So what they did is that they correlated geomagnetic data and correlated it with data for the velocity and the altitude of the satellite, and then from that they were able to see that from the onset of the main phase of the storm there was orbital decay that was observed in terms of the satellite. So the reason we're actually talking about this storm is that there is a spot that is called Air Race X. So if anyone is into Formula 1 racing, I think it's Formula 1 racing, but in the air. So Mr. Greg Ritz will basically just get into the nitty-gritties of how Air Race X works, but they depend on GPS in order for them to do their racing. So what happens is that there's 8 pilots that race in remote conditions, and they are supposed to finish that path in about 60 seconds with a speed of speed that may reach up to 400 kilometers per hour. All right, so in terms of observations, we observed a solar flare on the 9th of October, which resulted in what we call a coronal mass ejection. So what a solar flare is, it's sudden brightening on the sun that can affect high-frequency communication. But because it occurred in the night, the high-frequency communication over the African sector was not affected. The coronal mass ejection was of a speed of 1,200 kilometers per second, meaning that the time that it would take for it to reach Earth would be much more quicker than anticipated. So this storm actually impacted Earth late on the 10th of October. So from the imagery, you can see on the red image at the bottom, that's what we call a coronal mass ejection. You can see that there's these spots that occur on that coronal mass ejection. What in space weather terms, we call it a solar energetic particle event. So when this eruption happens, it comes off with solar energetic particles, and in some instances, those solar energetic particles can also affect high frequency communication and also affect the avionics in your satellites. So in terms of the predictions, we use numerical weather predictions. So the image that you see that is playing there, the movie that you see playing there is what we call the NLIL model. So what the NLIL model will do is that it will use initial conditions in order to predict the actual impact of the coronal mass ejection. It takes into consideration the speed of the coronal mass ejection and the angular width at that the coronal mass ejection left the sun with. From that, the spike that you see here is basically indicating the arrival time, the expected arrival time of the coronal mass ejection. Sometimes the error could be plus minus 12 hours, and we did see that this arrived during the day on the 10th of October. So this is just to show also what the other space agencies did. Can see from this imagery over here, this is the Space Weather Prediction Center in the US, and they gave a G4 watch. So what a G4 watch is for anybody that uses GNSS, that uses high frequency communication or power grids. So they can be aware that a storm can happen, that a storm will happen. And then this is also data from the bulletin from SANSA. This was released on the 10th of October, in the morning of the 10th of October. So because it was observed in the early hours of the 9th, at that point in time when the bulletin for the 9th came out, we were still, the other space agencies were still modeling the coronal mass ejection so that we can sort of be able to predict the expected impact and also the date of arrival. As you can see, it is highlighted here that we said that HF communication and GNSS would be affected. So this is two of the geomagnetic indices that we use. So these indices, we use them to monitor the progression of the storm. So this was basically two storms that followed each other. So on the 6th, there was the first storm, and then the second storm happened on the 10th of October. So when Mr. Greg Ritz from Team 77 contacted us, it was on the 10th of October. So during that point in time, we were expecting the arrival of the second CME. The first CME had already had some sort of impact and also affected the global navigation systems. So they had challenges with their GPS between the 8th and between the 7th and the 8th of October. That is when the first geomagnetic storm, which reached a KP of 7, occurred. So from this, we are able to see that the geomagnetic storm actually impacted the global navigation system signals. And then on the 10th also, they experienced some GPS issues. But then the storm recovered on the 13th. The competition was supposed to run from the 6th up until the 12th of October, but with the use of space weather information, they were able to extend the period of the competition up to the 13th. And as you can see from my slide there, the pilot, which is Patrick Davidson, was able to log a qualifying run, a very clean run, securing his spot for the final round as part of the top 3. Okay, so these are some of the products that were actually developed by SANSA researchers. This is what we call an Afritech near real-time TEC map. So this map basically looks at what we call total electron content. So from this movie, you're able to see that the total electron content varies throughout from the 6th into the 12th. So on the 11th, you will see that it becomes blue, which means that we were observing a depletion. So this depletion is what we call a negative ionospheric storm, and that is what also impacted the reliability and the accuracy of GNSS. Also, this was observed on the 8th of October, which is when they tried to do their qualifying rounds, and it was not successful. Okay, and then, so in summary, It's important to understand the impact that space weather has on the critical infrastructure that we have. So in most instances, obviously, we do focus more on the critical infrastructure, like your GNSS applications, satellite operations, power grids. But in this case study, we were able to see that it also affects sports, because they rely on the global navigation system. And then also to ensure the resilience of GNSS-dependent technologies, continuous monitoring is needed. Space weather forecasting is also needed so that we can be able to protect these critical infrastructures. So this storm is an indication also that in as much as space weather is a global phenomena, it also has regional impact, and with the limited cases that we have, this adds to the case studies that we can be able to use to prove to some of these industries that space weather does actually affect global navigation systems. Also, it's important that we have regular feedback between users, from users, so that we can be able to have tailor-made products for them, and also help them to be able to know which thresholds applies to them only. Thank you.
Okay, thank you very much, Witumelo. So our next speaker is Mr. Greg Ritz, and then he's just going to give us a testimonial of the space weather information that he received from SANSA and how it impacted their GPS navigation. Over to you.
Thank you very much, Mpho. Good afternoon, ladies and gentlemen. Listening to that, I got proper PTSD again. It was absolutely insane what happened. So thanks for letting me share this. I must tell you, I am on top of our friends group for popularity at the moment, telling everybody at the bar that I'm speaking at a space conference. It's, I just wish that my school teachers could be here. So, yeah, so thanks for letting me in as a civilian. It's absolutely incredible listening to the different heads of industry talking as to where we are as a country with our technology. It's absolutely insane. So, let me start off. Airrace X is a virtual reality VR experience that we are part of as a small team in South Africa. We are part of 8 teams across the world. The concept came from Japan and was born over COVID. So what is Airrace? There we go. Airrace consists of 8 pilots around the world, flying each one in their own country on the same racetrack against each other, and we have 10 days to fly. Huh? It's mind-blowing, and I'll explain to you how this works. We got 10 days to fly. Emma flies in Australia, Yoshimuroya flies in Japan, Aaron flies in America. We got Slovenians flying, Peter Kopstein, Martin Sonka, and we all fly the same track in different parts of the world. And I'll explain how we do this and why GPS is so important for that. Do I push the down button? There we go.
What is Airrace X Shibuya Digital Route? If we were to fly an aircraft over Shibuya, what kind of course design would allow for a spectacular race that would weave through the high-rise buildings? The Airrace X creates a racetrack meticulously, taking into account the topography of Shibuya and assuming that the race would take place in real life. Based on the Shibuya course design, each pilot will fly at bases worldwide. The flight data acquired from these flights is converted into images using XR technology. The system allows the spectators in Shibuya to watch the race as if race planes flying on a smartphone, tablet, or head-mounted display with the real metaverse platform, Styly.
I mean, at first, we've been doing this since 2023. At first, this wasn't really, I didn't comprehend it because it's not something that we are used to in South Africa. It's an Eastern thing. It's for Japan. It's for the generation that is completely on their phone the whole time. They can walk through Shibuya intersection and watch planes fly in real time, but not really. It's mind-blowing. So how do we race in South Africa and around the world? We get sent a course, a layout. Then we get sent GPS coordinates. The GPS coordinates lays out the track at our home field, exactly the same as all the other pilots around the world. This track has got deadlines and is manipulated to fit within the street circuit that they have chosen for this event, so that the pilots don't fly the real plane through the real building imaginary. We then get sent how the course is going to work. They sent us a layout as to how this course is laid out in the city and also what it should look like on our airfield. We take those GPS coordinates, I take it, and I take my Garmin watch, and I put in all the coordinates in my watch, and I walk and I mark out gate 1, gate 2, gate 3, gate 4, and the pilot then inputs those GPSs into the race computer, which we call the RDU unit, and the aeroplane makes sure that he gets penalized if he doesn't hit those markers. So the computer makes sure that we're hitting the GPS coordinates that are given to us, and the pilot flies it according to ground markers that we put out on the ground. This is what the ground markers look like. What we use is we use 2 drums, paint them white, and we do 3x3 ground markers on the ground. The pilot will then fly past these at just over 400 kilometers an hour, 15 meters above the ground. And this is what a practice flight would look like. Very tight flat, very tight course. The course is about 850 meters, and we spend 60 seconds in that track. What the pilot then hears in his headphones is with a token that we loaded to tell the unit where we're flying, he can hear too high in the gate, pylon hit. If he cuts a corner too sharply, you get a pylon hit. If he climbs in the gate, too high in the gate. So the system, with the use of GPS technology, manages how we fly and how accurate we do it and how fast we do it. And you want to fly as fast as possible. You want to have the faith in your markers and your GPS locations that you can cut the corners and get as close to that imaginary pylon as possible to get the fastest time in the world. At this stage, we were lying second overall. So, fly as fast as you can. We then upload all our flights. We can only see the other pilots' practice flights and qualifying flights. After that, we don't know what anybody else flies. We fly a quarterfinal, a semi-final, and a final. Everybody flies them. And you only find out when they do the live broadcast what your time was. So it's really, you're sitting at the edge of your seat. We don't know. We know what our time was, but we don't know what anybody else's time was. And then they promote the race like this. It gets streamed live on YouTube.
Get ready for a blazing new season of Air Race X kicking off on April 29, 2025 in Fukushima, Japan. Elite pilots from across the globe face off against daring newcomers in the ultimate test of speed, skill, and precision, decided by mere thousandths of a second. Watch rising star Aaron Deleu, Australia's aerobatic prodigy, make his explosive debut, pushing limits with his mantra, calm, crisp, and clean. And cheer on South Africa's very own Patrick Davidson, backed by a nation roaring behind him, as he aims to soar even higher after securing third place in the 2024 season. Fukushima, a symbol of renewal, sets the stage for a season of epic rivalries, jaw-dropping twists, and high-stakes drama. Catch all the action live on Air Race X YouTube. Experience the future of motorsport, where cutting-edge AR and digital twin tech bring the action to you, anywhere in the world. Join us at Fukushima Sky Park for an electrifying public viewing event as local hero Yoshihide Naoya defends his title and ignites the race for the championship. Buckle up. This is just the beginning of a season that will redefine limits. Air Race X, expanding possibilities. Tune in and feel the rush.
The footage that they use after they capture all the GPS data is real footage of the actual flight. We're now using tail cams on the back of the plane that they overlay, and you can see the other plane passing you during the broadcast. It's absolutely phenomenal. These guys are so clever. So, Team 77 against the rest of the world. Well, that's what we thought October last year, but instead, it was Team 77 against the GPS. And it was, we took the whole plane apart. We didn't know what it was. This is a video where we're just looking at the Garmin unit on the plane, and we're just looking at all this GPS satellites just disappearing, getting a signal, losing a signal. That's our RDU unit, and it's on yellow. It needs to be green. We don't know what to do. So what do we do next? We blame our GPS. That's Mark Hensman. He's an absolute genius when it comes to aeroplanes and that. We did the actual real Red Bull Air Race circuit in 2018, 2019, and that's where we found him. He's absolute machine. That's our race plane. We took our race plane apart. It takes two guys about 3.5 hours to take it apart. Consulting with a team in Japan, we used a Red Bull can that we cut up to put underneath our GPS receiver just to isolate it. We turned off all the Wi-Fi, Bluetooth connections on our GoPro cameras. We took them out of the plane, and still nothing's happening. It's heartbreaking. We're losing. We got 2 days left, and here we can, a small South African team working out of a hangar in Grahamstown with a bunch of donkeys around us that's eating our cars, trying to compete to the rest of the world, and our equipment's not working. We're sitting in the middle of nowhere.
It's pile on it after pile on it. Back deviation to high in the gate, to low in the gate. It's the final race for 2024 series of Air Race X, and we just cannot make it work.
I'm Greg Ritz, team manager for Team 77. So 13, 14, 15 practice flights down, and we can't get a clean run. Patrick, the pilot's conference is going, myself, Mark, trying to isolate the problem, thinking it's a GPS receiver. We're on calls with Air Race X, with Ben and Aaron, trying to find a solution, going through the readings. And while we're waiting for that, I go onto my computer and I start Googling GPS deviations. What can cause bad GPS readings? And right there, in front of me, we are flying during the second biggest solar storm in 2024. And that's when I found them, the South African National Space Agency.
Hi everyone, my name is Predictition, and this is and we are space weather forecasters for the South African National Space Agency. So when Team 77 contacted us, we had to make sure that we understand what their problem was, so that we can be able to give them accurate information and accurate space weather information, so that they can be able to make informed decisions and also be able to fly in the limited time that they had.
It's a privilege for us to have SANSA on board with us, them showing interest in our sport, enabling us to get accurate weather forecasting, especially out of space, which I didn't even think was something relative to our sport. But yeah, having them on board with us has made us a lot more efficient with selecting the correct days in order to do our races, our practices within the race window that's given to us.
So yeah, October 2024 is when I discovered SANSA, and it's been An absolute incredible journey. I mean, in Hermanus, really? Do you know that feeling when you pick up the phone, you're phoning an organization, you got the number on the website, and it's, I think it was late in the afternoon, and somebody actually answers. and they're actually working with you, and they got a night shift team, and they understand what you're doing. It was incredible. I mean, now we're getting forecasts like this. Well, I don't look at the forecast, I just phone my forecasters. So yeah, to SANSA, thank you very much. Yeah, you've taken the worry out of it for us, and we really appreciate it. Thank you.
Thank you very much, Mr. Greg. So thank you for working with SANSA in showcasing and working together to show that space weather has impact on GPS, because sometimes it's difficult for us to find a real-world example of the user impact of space weather information. So the next speaker is Nkosinati Masango, and she is going to talk about the importance of us having ground-based instrumentation to monitor space from the ground. And the reason why we have this instrumentation is because the space weather impact can have a regional impact. It can impact different regions in a different way, and we need this ground-based instrumentation to monitor space weather. So over to you.
Okay. Good afternoon, ladies and gentlemen. As introduced, my name is Nkosinati Masango, and I'll be telling you why we need instruments on the ground, even though we do get satellite data that helps us to make these type of forecasts for our clients and potential users to make some informed decisions. Right. So, as much as space weather is something that happens in the upper space, it's quite important for us in a sense that right now, most of these satellites really help to make people know what to do. I think that's very important. People need to know what to do. So yeah, that's why I'm in this career. I just like telling people what to do. So I wanted to take something that will also, give me some money. So I tell people what to do for a living, and yeah, I'm happy with that. So the process of forecasting, it's not necessarily space weather forecasting, but you need observations, both satellite and ground-based. You need somebody to analyze the data, which is also a forecaster. And we also have your numerical weather prediction models. Those are models that they use to put in these observations. So those initial conditions, they are put in that computer, and so that you can project what happens in the future. So that it is quite important, because our end product is what our users use to actually make decisions, which is quite important. So what are the benefits of having just space weather forecast, space weather observations? In essence, you need to see for you to know what's going on. It's like a person. If I tell you that this person is not a good person or something is wrong, you wouldn't take my word, but you'd want to be with the person all the time. And then that's when you can be like, oh yeah, but she was saying the truth or not so much. So it helps us a lot, because we want to better understand space weather effects, since even though it's a global phenomenon, locally it might not look the same or have the same intensity. And also, you also want to improve your system design, which is what you use to predict your forecasting. And also you want to have an efficient warning and predicting system, in a sense that if you have so much observations, the more you see, the more you can say, I guess. And you also want to issue accurate forecasts, and it's also an opportunity for international collaborations, in a sense that if you have data and another organization might be interested, they might have maybe capabilities that we might not have. So maybe they have like some research experts there that we currently might not have, and because we have data that we can exchange, they can actually help everyone to improve. Right. So I'm just going to explain to you the type of ground-based instruments that we use or that I normally use all the time to help make these type of forecasts. So we have what we call the ionosonde. So the ionosonde is a ground-based instrument that measures what we call the electron density. So if you can look on this image, for meteorologists, you are mostly concerned about this graph here, where your graph for your atmosphere is a function of temperature. So you know the higher you go, the colder it gets. So it changes with temperature. For us, it's different. We look at something similar, but we look at a different parameter in a sense that we look at what we call electron density. So your electron density will vary with height. So now, what happens with this type of instrument, this one here? It looks cheap, but it's very expensive. This thing is very expensive. Ionosondes. So it's actually, we are quite fortunate to have such a thing. So what it does, it measures, or it takes frequencies at different heights. So what you would do, it's like you send a pulse in the atmosphere, and then what happens, the time delay, so it will go up and then come back. So as it's the time delay, as it measures, you will get frequencies at various heights. For instance, so as your frequency goes, it comes. As it goes, it comes back. Then it maps out what we call an ionogram. So an ionogram is just a picture that is done by your ionosondes. So why we really love this type of instrument or the type of data it gives us is that it gives you a detailed version of what the ionosphere does at different heights, something that a satellite does not give. Yes, a satellite can cover a broader space in a sense that it's high, and it's able to capture larger data, but it does not get to tell you in detail what's happening where, because this is just like a vertical incident where you have a pulse and you get to see what happened on that time or on that day for that particular location, for that, what the ionosphere was doing for that location. So unfortunately, the limitation of it is that it can only measure up to a certain height, which we call the critical frequency, also known as the F0, F2. It's a very popular word for us in the office. So what it does, it's like your pulse would keep coming back. So it will go, reflect back, come back, until to a point where it can't do that anymore. That's where you'll get your critical frequency, and usually that's where your F2 layer is. So that's where maybe it will stop, and then, for instance, there. And then after, this is just the model side of it. So this is just it's derived. The top side of it, it's quite derived. So if it's something you think you are not maybe necessarily might use the end product, in terms since you might not be using space weather other departments, it's very important in terms of people, maybe if you can see that your relationship is suffering, make sure that the critical frequency is always high. Because remember, if your frequency goes low, then they will, yeah, that's why we don't have those problems as forecasters, because we always know where the critical frequency is. So make sure it's high. The higher it is, the better, because now you can have higher frequencies going up. If it's low, it's gonna be tough. I don't know. There's another one, GNSS receiver. So, you know, with a satellite, you need a receiver on the ground to be able to capture that type of information. Now, what it does, when the signal moves from your transmitter, which is the satellite, going down to your ground-based instrument, which is your GNSS receiver, the time delay for it to move from the satellite to the GNSS receiver, it's equivalent to a parameter that we use to measure the ionosphere, which is called total electron content. So the time delay, it's equivalent to that total electron content. And that's something we use to monitor the ionosphere, because depending on what happens, remember, if you have these types of storms, these geomagnetic storms, two things are going to happen to your electron density. It's either going to increase or decrease. So that's something, and because of it increases or decreases, that's when you get some problems. So we want it to be as normal as possible, or we try. So this is just one of the instruments that we have also to measure, and it's also very important in a sense that it helps to make this type of product. So like my colleague said, with it's an Afritech model, near real time, you get to see what the ionosphere is doing at the time for that particular region, which is in the southern region. So yeah, that's what we normally use it for. And yeah, so what do the instruments do, or how do they help us? So now what we have here, it's just data. Oh, okay, I don't know what I did, but yeah. What happens here, this is just data that was derived and calculated using these type of instruments. So how it will help us? Remember, like I said, you want to know when your ionosphere is normal, because when it's normal, then you can make good decisions, or it helps you to make some nice decisions. So the first image, it's what we call total electron content, like I said. Since it can measure only, the ionosphere can measure only up to a certain point, which is the F0, F2, the critical frequency. This is just one of the TECs that was derived from that ionosphere. So the red, it's red, it is red. I know from the back it looks pink, but it is red. The red-pink line, that's when we do some calculations where you want to calculate your deviations. So deviations are very important because you want to know, like I said, when the ionosphere is quiet. So now that's the monthly median. So the pink line will tell you when the ionosphere is quiet, you don't have any issues. And then now the black dots, it's when actually what was happening with your TEC at the time. That was actual data on the time there was a storm or not. And this is the second one, that's your critical frequency. So the red line will show you the critical frequency values when it's quiet. So that's also something we calculate versus what it was like. So you can see as the days went by during the time of the storm, you get to see your critical frequencies either decreased or they increased, as well as you see your TEC, your total electron content decreased relative to what it was supposed to be. So these type of data set is quite important because for us, you don't want science, you need proof. You cannot just look at something and say it's going down or it's going up. You need to quantitatively have a measure for it. And if you have enough data, you can do some statistical analysis. That's where this image comes from. So this image comes from, in a sense, that when you have this type of data, you are able to conduct such research where you get to know the thresholds. So for instance, the thresholds of critical frequency and the total electron content might not necessarily be the same. For critical frequency, your deviations would be plus minus 20%. So if your critical frequency stands within that plus minus 20%, it means there's nothing, it's okay. Your critical frequencies are fine. But once you have storm, you can see they start to, which is the blue line here, the solid line, they start to deviate from those deviations from what it could have been normally. The same would happen with your total electron content, which is the dashed line at the top, which is plus minus 45. So you can see that during quiet times, most of the time they fall within the thresholds, but if there's a storm, they can go either below or above the thresholds, and that's when you can quantitatively say there was a storm at the time. So the reason also why this was also a special case, because they were flying in Grahamstown and we do have enough sufficient observations, we do monitor it most of the time, we were able to do such, you are able to see such statistics. So this is one of the SANSA's instrumentation projects. So what happens is that they're trying to deploy these type of instruments, your GNSS receivers, your ionosondes, those types, so that you can get to see observations for the whole of Africa. But it's done in a strategical way because now they're focusing on the SADC part as well as on your equator sides. The reason being is that we have what we call equatorial ionization anomaly. So it's like, if you think about the normal forecast, where you have the ITCZ, the intertropical convergence zone. So that's where most of these storms are at their highest, or they affect most of the time. So if you have this type of storm, your equatorial ionization anomaly will expand. So now it means that now those effects will start to propagate towards your mid-latitudes or lower latitudes and mid-latitudes. So as you can see, there is evidence of one of our GNSS receivers. You can see that on the day of the storm, for a mid-latitude station, which was Hermanas at the time, it was low. But when you get to see another station in Nigeria, you can see on the same day the TEC behaves differently. So different regions have different phenomena or impacts. So based on that, if you have enough you have done enough statistical analysis, you might be able to help people on making more informed decisions. Another one we have is an ionospheric scintillation receiver. So the same way, it's the same phenomena if you think about it. Remember, with when you have these type of storms, what happens with your signal is that it's either your signal will get delayed or your signal also gets contaminated. Remember, when the signal moves in the ionosphere, it starts to interact with your electrons a lot, your electrons and ions. And the more it goes, it means your signal starts to get either compromised or the quality degrades. So you end up having some issues like loss of lock in terms of your GPS signals. So this is also one of the products that SANSA does. It's scintillation product where it's measured by the two indices, your S4 indices or your amplified index. So indices. So what happens is that on this picture you can see if you have disturbance or there's a storm or something happens, you get to see that the signal, your signal starts to get contaminated, if I may use the word, versus when it's just a free flow, it's just a clear reception. Now because it is embedded with these electron content, total electron content, or these electrons, now it becomes quite unreliable. So maybe that's why sometimes your GPS might not be working, or you might get a wrong direction in that sense. So we do have these thresholds. These thresholds, they are also, like I said, you derive them from statistics, but also from end users, because now you'll be able to classify to say, okay, this type of storm, maybe if you have like a minor storm or an extreme storm, you're most likely to get strong scintillation. What does strong scintillation mean for maybe people who are using GPS or people who are in the aviation industry? It might be different depending on the thresholds that they have and what you use it for. So in conclusion, it's just to show that as much as space weather, it's a global phenomenon, it can react differently for different regions, and the importance of also having ground-based instruments so that we can also have our own things. And yeah, so thank you very much. And yeah, thank you. Is it
Okay, thank you, Nkosnati. Our next speaker is Colonel Mark Wilson, and he's going to talk about the benefits of informed decision-making in aviation industry.
Good afternoon, everybody. Allow me to stand on the protocol that was observed earlier today. I'm Colonel Mark Wilson, currently the Senior Staff Officer for Air Combat Planning in the Air Force, doing strategic planning for the combat operations up to 2080 and beyond. And also my second hat that I wear is I'm second in charge of the Space Command implementation team, so working closely together to get the Space Command implemented. So today, my talk will be on that, the benefit of informed decision-making. So aviation being quite a wide field of view, we've seen some from virtual flying, there's civilian flying, you have your commercial flying, and of course military flying. And all of those, you have different platforms in all of those. So I'll try and cover a broad spectrum of all the aviation areas that get affected by the weather. We'll look at those implications, and then right at the end we'll just look at some of the benefits. Then if we do have this proper weather forecasting of space weather, what can that do to aviation weather terrestrially? So looking at the effects of these weather, a lot of the speakers before me today already spoke about this. We definitely have effects on your communication, specifically looking at high frequency or HF communications. Of course, those are used for long range communications of aircraft between ships, land forces, not just aircraft, as I said. So, and those are normally at your very low frequencies up to about, yeah, well, what gets affected, sorry, is from the space weather up to 30 megahertz is where those frequencies get affected. So from the space weather forecast, what they can predict for us is what frequencies will bounce from the ionosphere and what will not bounce. Because that is what actually with the HF frequencies give you your beyond line of sight communication capability. So if you have, with our ionosphere is disturbed and the waves don't bounce like they should, you are not getting communication where you're expecting communication to happen. So that is one of the benefits of space weather prediction, is that we will know what frequencies in the HF band you will be able to speak with. And also for your transoceanic flights, for commercial flights, there are some regions where you just can't speak with normal line of sight radios, your normal very high frequency or the ultra high frequency bands, which are up to the 300 to 400 megahertz bands. Those are line of sight, and basically over the sea you will not have a ground station that will be able to speak to an aircraft, so hence they fall back to the high frequency or to satellite communication. So in all cases where we have these communication failures are because of these ionosphere, on the ultra high and VHF and UHF content, where the actual waves get disturbed. So your receiver, the waves that are transmitting through the air are not coming through to the receiver the way they were transmitted, and you sometimes will not have clear communication. So the L-band satellite communications, again, it's a function of the ionosphere and the waves coming through there, is that you're getting disturbances and you are not getting the communication that you're expecting. So your commercial flights, where they might rely on satellite communication for in-flight position updates or for transmitting some of the telemetry data of the engines back real time, that cannot happen if you're not having that communication properly. So in terms of navigation and GPS failures, I think we've had a proper explanation of exactly what happens to that. It's timing errors that happen, and GPS is based purely on the timings, the time you expect the signal to arrive, the time that the signal does arrive, and if there are differences in that, then your GPS position is not where you're expecting it to be. Of course, in aviation, it's a redundant function. It's designed to be safe with fallbacks. So mostly some of the more commercial and military GPSs, we have fallback functionalities, a function called the RAIM function, which is your receiver autonomous integrity monitoring functions. So that's predicting when you are expecting the satellite signals to be in view. So you need a couple more than you normally. You need 4 satellites to get your GPS lock, but that one will then take a 5th or 6th or 7th satellite if they are in view to make sure that the position that you are getting is correct. So there are backups in aviation. Of course, talking more from a military point of view, we actually plan to fly in GPS denied areas. So a GPS failure for a military pilot should not be a problem. For civilian pilots, and if you fly in competitions, of course, that makes a lot of sense. But we plan to fly our missions even if you do GPS denial. So if they're predicted for us, it might not, in that case, mean that you won't do a mission. You might just delay it or make another decision. But we'll get to those decisions at the end. In terms of aircraft avionics systems, again, we've spoken about these electric content or the increased electron content. What the research describes is that there are some states where you could actually get in the transistor down to the 1 and 0 bits and bytes level, a change in the transistor from an increased electron content change. So when you design a piece of hardware or firmware to do something, this solar storm comes through and it changes your electron states inside the transceivers. So that is definitely something that can change. And if you think about all these digital cockpits that are out there, commercial flights, if you have an engine critical control panel that sort of all of a sudden the state of one of the transistors gets changed, that could become it could switch the engine off, for instance. So there are definitely effects in terms of avionics and aircraft systems that can be affected by these solar storms. In terms of the static buildup, again, some of these avionic systems or aircraft are designed to dissipate these extra electrons, but sometimes the content is so high, or the concentration is so high that you cannot get rid of all of these electron buildup, and you might get arcing or sparking on some of your components that will also then degrade your system further. In terms of the radiation, it's something that not a lot has been spoken about today. Typically, there are rules and regulations about how much exposure, radiation exposure, each human being is allowed to have in a year. So if you think about how many X-rays, that's why they measure how many X-rays per year you actually take. When you're doing high-level flying above 26,000 to 30,000 feet, you are getting exposed as a crew and as passengers of aircraft to additional radiation. So there are airline restrictions that said if you're flying above those levels, they cannot expose the passengers to additional radiation. So again, these solar storm predictions will then tell you where these increased radiation levels are, and airlines might have to make a decision to abort a flight or to route around an area where that is increased radiation is experienced. And again, as it was alluded to earlier as well, this is more prevalent in your polar regions. The mid-latitudes are not so much affected by electron storms or the solar storms. So for transoceanic flights that do cross over polar regions, that is more of an impact than for mid-latitudes. In terms of the implications of these phenomena, so as we said, for communication, yes, there are fallback methods. You could, on HF, go to a different frequency. You could use satellite. Excuse me. So yes, as I said, aviation has got fallback modes, and we always plan to have redundancy. But for air traffic management on the ground, that might become a problem. There are radio failure procedures that are in place for any flight that loses communication with the ground control or with air traffic control. But that has additional impacts on all the aircraft that come behind you. The separation between the aircraft in terms of time and heights get affected. Those cause delays. All your passengers on the ground get grumpy because they have to wait for another flight that's not in time. So all of these impacts are things that do affect the solar weather, that could affect general aviation. And the more and more we get reliant on technology, especially for civil application, we use GPS approaches. They're trying to reduce time between aircraft, so trying to get more aircraft on the ground in sooner times. And if you have then a loss of communication, those areas or the timing must increase, and it has impacts on economic impact on how many passengers you can fly. In terms of navigation, as we said there, for GPS, it's not just used for position, of course, it's used for timing and for navigation. And as we also heard earlier today, banking applications, there's a whole lot of other things that get affected by by GPS signals. So I think I've said enough on navigation or the impact thereof. Again, just what I want to say in terms of military applications is that we do train to fly without a GPS. So it's not a huge impact for military. Civilian, yes, for airliners, they might have problems. They also have dual redundancy. There's also in aircraft what we call the inertial navigation systems, INSs, which make use of gyros and ring laser gyros to get your position if you don't have a GPS. And what technology or what research is working on now is what they call a quantum INSs. So they give us even more accurate position and navigation without GPS. So a lot of what we've seen in the Russian and Ukraine conflict in terms of GPS jamming for UAVs and all kinds of other jamming is that you probably will not have the use of GPS in a conflict. So most of the research now in weapon systems are going into targeting without GPS applications. And then in terms of radiation, the impact there, of course, is the increased exposure. Like I said, if you do fly through these areas where there are increased exposure, your passengers might be exposed to higher radiation, which could, of course, lead to litigation. So that is definitely something that the aviation industry would want to avoid. So what can be done about it? What is it that the aviation community can do? In terms of the avionics, the aircraft design, or the avionic designs, there's definitely some hardening research that can go into making the avionics more robust, making sure that these electron content increases don't affect your avionics, that we don't have failures, or that you do have backups, systems that are cross-checking each other to make sure that you do not have failures. In terms of flight planning optimization, as I said, airliners, their business is making money. So if they are flying, if they have to divert, if they have to fly longer routes because of a storm, that all impacts on their profitability. So the more that you know about these storms that are coming, the more you can plan, the more you can prepare, the better for your profit margin. In terms of operational costs also for the Air Force or for any military, I mean, if you do not have to have a flyer mission exactly at that time, you could opt to delay to save your equipment or to save the mission. Sometimes we don't have that option. Sometimes we just have to do it. And then the reduced exposure, if you can avoid an area where there is increased electron content or the radiation, then that is something you can do for the passengers. In terms of shielding cockpits, the Gripen cockpit, for instance, is shielded. So there are some things that can be done to harden your aircraft as well to these storms. In terms of decision making, if you have proper forecasting, you can make proper decisions, and again, so that will avoid litigation. It could keep the aviation safety record where it is. The aviation industry has got very good safety record, so we would like to keep it that way. From research that I did, I couldn't find specifically this time period, October 2024, there were not one specific aviation incident that was attributed to the solar storm. Even though it was one of the biggest storms in the history, there were no aviation incidents directly attributed to that. Yes, loss of GPS, loss of lock, loss of communication, but that did not lead to aviation incidents per se. Then in terms of the equipment, again, this on the ground, we've seen the systems that SANSA uses to predict this weather, but also your instrumented landing systems, the VORs and TACANs and DME equipment that the normal aviation people use on the ground. All of your ground equipment gets radiated extra during these high storms. So your life expectancy on technology and on chips, those things decrease the more you have solar or weather phenomena like this. We've spoken about the aircraft, the static buildup. avionics, those things can be affected. So your lifespan, again, the more you expose your equipment to these higher electron levels, you shorten their time span or their lifespan. And then again, for us planning to put the satellites into space, space weather becomes much more prevalent in terms of satellites. The solar storms, the solar winds, if you go to the, I think we'll have a discussion on the dashboard later, but at the SAF stand there is a dashboard display about the solar winds. So those things are used in collaboration with keeping your satellite position in its orbit. So the stronger the satellite or the stronger the solar wind is, the more energy you have to expend to keep it in its orbit. And you have a very limited amount of capacity in terms of power in a satellite. So then you have to take that power resource in terms of not being able to do, using it for sensing, but positioning of the satellite in its orbit. So there's a whole lot of these things that the more we know about the solar weather, the more we can plan for it. And then again, for the military, the benefits of it is that we will have mission success. I think for civilians, it goes about profit margins. So the more they know, they can plan better. They can make sure that their profit margins are where they should be. And I think for the civilians, sometimes you have to delay your competition, or you try and fit into your competition, or you make use of other means. You go back to the old ages of having a map and a stopwatch, maybe going back to normal star tracking and doing it via stargazing. So in terms of aviation, I think, yes, there are impacts, but I think the industry is well positioned to have fallbacks and redundancy. But we look forward to working more closely with SANSA in terms of getting the forecasting and the impacts on aviation. I thank you.
Thank you very much, Colonel. Our next speaker now is the second session for Earth observation component, Mr. Buloko Sibake. He's going to talk about the updates on the development of the South African Earth observation systems of systems.
Okay, thank you. Good afternoon. I hope you can all hear me. I'm here to talk about, update you as far as the development of the SARS portal is concerned. SARS portal is a project that comes a long way. It's more like a household name for the Earth observation community. The reason why I'm saying that is because the project that we are implementing, it comes at the back of the strategy that was developed as far back as 2007, called SARS strategy. So what the strategy basically say is that we need to get together as the Earth observation community, bring the data that we all produce, put it in a coordinated center where it will be easy to discover, easy to search, so that it can be used, so that we can create value out of it. So in terms of the SARS portal, basically SARS portal is a South African Earth observation system of systems. It's a centralized system meant to integrate all Earth observation systems in South Africa. It's a system of software components that work together in unison to create this centralized geospatial repository. Yeah, but it's not just limited to geospatial, it's over and above geospatial repo. It will integrate terrestrial data, I'm talking about land, maritime, air, as well as data that has been sensed by remote satellite, remote sensors onboarded on satellite from various data custodians within the country. So it will harvest and aggregate EO metadata. It will not aggregate the actual data per se, but rather the metadata. Through the metadata, those data sets will be discoverable, searchable, from a central location. So it will be an entry point to find Earth observation data or Earth observation systems within the country. So this system shall be called a one-stop shop system. From that system, we'll use it to discover the data, information, knowledge, understanding about the physics of our planet, physics fundamentally defined by energy, matter, space, and time, the chemistry of our planet. Normally, chemistry, you all know chemistry defined by the states of matter, where we focus on the matter, liquid, gas, and solid, and the other states that the sun people know it very well. And as well as the life, which is the most important part, the advanced life here on Earth. I believe we all know this planet is the only planet that we know is the one that can sustain advanced life. That is the biology. That is very important. In different, we have got different forms of life, which is the plant, animal, and human, as well as the geography, which is very, very important because it tells us where things are, where they're happening. It gives us the geometry of our planet. And for me, it gives us the global perspective of our planet, so that we are able to manage our environment, manage our resources, deal with the issues of health, safety, and security, with the data that will be harvested or discoverable from the portal. One will be able to innovate. Once people have got data, then you'll see ideas coming through. You'll see people working on the data, innovate, and also that will drive economic growth. And also it will assist us in dealing with issues of climate change. And even when decisions are made, it will be informed by data, be it decisions about policy or any other decisions. So in us developing the portal, it will be developed within the boundaries of these legislative and regulatory frameworks, such as promotion of access to information, whereby the Act says everybody has got right to access information, especially information that has been collected by the state. And another one is the Land Survey Act that sits under the Department of Land Reform and Rural Development, as well as how we're going to project and make sure that data that we share is interoperable. So we'll make sure that whatever metadata sets we publish are compliant to Special Data Infrastructure Act, also sitting under the Department of Land Reform and Rural Development, or any other legislation, such as your Scientific Research Council Act, South African Weather Service Act, Chapter 14 of National Water Act, and etc., including POPI Act, Protection of Personal Information. So the success of this portal hinges on the support and participation from these stakeholders. So this is not a comprehensive list. It's not the exhaustive list of all the stakeholders. The first stakeholders being the Department of Science, Technology and Innovation, which is the funding agency, This project is executed as stipulated in the SAIS strategy that was written back then. It was conceptualized that one day we'll have a national space agency that will execute the implementation of the SAIS strategy, SANSA, as well as the data custodians, those entities that will contribute, or individuals that will contribute data to the portal in the form of metadata, so that that data is easy to find or access. We're also working with SION in terms of data policy and EO metadata curation, as well as EO economy, EO community as large, such as community of practice, group on Earth observation, the global one, AfriGeo, which is the same as, but is a South African one, is the same as the GEO, which is the South African one, African one, SAGEO, which is the South African, academia, CSR, and or any other research institution. So in terms of the system, how it was conceptualized then, this is the high-level system architecture. I hope you can see. At the center there is the SAIS portal. That is the system that we currently building. That system will be hosted in a data center. That data center is currently located at our space operation at SANSA. So that SAIS portal will integrate data sets in the form of metadata from various data custodians, and it will be accessible from that central location by any user that requires that data. So we'll also integrate GEO, which is a global Earth observation system of systems. I think the idea of SAIS, that's where the idea of SAIS comes from. So in terms of the data sets, I hope you can see data sets that we have identified and that we will integrate. Obviously, this was written back then. This will be updated. Data sets about the disaster, data sets about the food security, data sets about the land cover, data sets about ecosystem degradation, data sets about the air quality, data sets about environmental related health and diseases, climate change, socio-economic data needed for application and interpretation of Earth observation, and your normal geospatial data necessary for organizing and displaying Earth observation. So in terms of the project status, the system currently it has been deployed online. You can access it even now as a beta vision. We're calling it a beta vision because we don't have all the data sets to declare it a release candidate, and also we're still dealing with other technical issues on the system. So we're busy adding metadata to the system. We added quite a few on the system. So we're targeting to have the release candidate deployed around September, the final release to be deployed in November 2025. In terms of the system going forward, once the system, we have created that baseline where people are able to use the system, then we'll keep the system operational and maintained, improve and optimize the system and each dashboard, obviously, in conjunction with the users. where those changes or updates are informed by user requirements, optimize the system for mobile access and interactivity, make the system even more scalable, arrange data by thematic areas. As the system grows, then we can incorporate AI-driven analytics and also image recognition. Then we'll continue engaging the stakeholders and adding more data sets as per the science strategy and over and above that. And also in the future, we're looking for people to be able to access data through the portal. Not necessarily that will host the data. We can do it in a very distributed way. Even though your data is hosted in your private system, but through the portal, it can be made to be accessed and also be extended to other systems for more innovation. I think that's I have from my side, my ending statement. So even though we live in an uncertain world, that's what I meant. Probabilistic world. Yeah, so you all know that the world that we live in is uncertain, but as long as we stay determined and coming together, we can navigate through it. Thank you.
Thank you. Our last speaker is Dr. Cecilia Masimula. She's going to talk about autonomous agents for monitoring agriculture and natural resources.
I need to, because of my height. Good afternoon, ladies and gentlemen. Before I start, because I'm going to talk about AI, how we can leverage AI. So I just want to know who's still reluctant to use AI in 2025? Who said, no, I don't want to use AI? Oh, okay. Okay, then I'm not alone, because I use AI, but I use it responsibly. I have my own AI, like locally. I don't use all other AIs. I have my own locally. So I'm going to talk about autonomous intelligence for agriculture and natural environmental resilience. I changed to my title because I felt like that one, it was not the way I wanted it to be. Okay, how do I use this? Yes, there's a button. Okay, I'll skip this one because you know our mandate, and also in the morning, everybody from SANSA talked about our mandate. How? It's not changing. Oh, okay. So this presentation actually is not like presenting, because I'm going to talk about showcasing, like this session, they call it showcasing. So it's divided into two. First, I'll talk about our current project at SANSA EO Group. So we are busy with decision support tools. Okay, this thing, I don't know. Okay. So this is our decision support tools that we're busy with. Actually, 3 of them, agriculture, air quality, as well as the disaster. And no, sorry, not agriculture, but air quality, disaster, and water quality. Agriculture and built environmental will start next year, the next financial year. Okay, I just put a video of our landing page to see it. Okay, this is a air quality monitoring tool. So this one is actually based on satellite. We know that we have a lot of air quality monitoring tools, but most of them, they're based on stations that are scattered around the country. But this one is unique because it's based on satellite data, which means we cover the whole area. So the phase one of air quality decision tool is actually completed. We are now busy preparing to start phase two. And what we monitor, we're going to monitor is pollutants such as sulfur dioxide, nitrogen dioxide, carbon monoxide as well. Yeah, those ones. To enhance decision making, the system is going to be interactive or is interactive. National scale monitoring, like I said, we're using satellite data. So we're going to cover the whole country, and also to make sure that we have tools that are essential for environmental management, public health, as well as policy making. Okay, now I'm going to talk about the AI tool. So I call it this agent, Eco AI Africa. So this is autonomous AI agent protecting South Africa's natural heritage. So I know that every day we get emails, automated emails. Those emails, most of them, they're actually sent by agents, AI agents. We get calls sometimes when you answer, nobody is talking because of those calls are actually started by agents. So this one is actually agent for environmental monitoring. So why SANSA is actually in the good space to actually develop this. We know that SANSA, we are now 25 years, plus or minus 25 years. And then we have data, historical data, because you cannot talk about AI without data. There's no AI without data. You can have all beautiful models, whatever models, but without data, there's nothing you can do with these models. So we have data, and then actually our government mandate for monitoring, environmental monitoring. And also we have, we are actually leading space agency now in Africa, or SADC. We partner with a lot of governments as well as even private organizations, as well as international. We have international partners, and also we have ground stations like what my colleagues actually presented. Here is just to say SANSA is actually we unmatched competitive, we are in an unmatched competitive position because we have infrastructure, government official mandate for environmental monitoring as well as national security. And also we have data. The most important things, we have data. And also continental credibility, technical expertise. We have localized models. We don't just rely on global models. We have models that are localized. Yeah, and also we have a lot of strategic partners. Okay, the reason why I thought of this is because of these problems listed here. Fire, always, every year we talk about, especially this time, because it's a windy time, it's after winter, so you start hearing about fires. Forest, woodland, they are decreasing because of farming as well as expanding settlements. Cities, they're experiencing high temperatures, they're becoming hotter and hotter, so we need this kind of AI agents. We have problem of coastal erosions, drought. I think we still remember drought, 2015, 2016, 17 drought. Even now we're still experiencing drought now and then. Agricultural losses, we lose billions annually due to changing rainfall patterns, and also mining and industry, they're polluting. When you go to Wheatbank, you can just smell because of pollution from mining. Okay, the reason, this one is just to explain that, to show that we do have we can have localized AI agent. We don't have to rely on other agents, so we can have the one that are developed maybe by other countries, or so we can have our own localized AI agent because we have our own data, we have our own models, we have weather stations like SOURCE, we have cloud computing infrastructure because sometimes AI like consume a lot of, need a lot of space and computing infrastructure. Okay, we have localized geospatial models. We've been working on a lot of rangelands. We have papers on rangelands monitoring, quality, and also productivity. And also, local language, we need something that we can actually, we get information using our local language. So I know that University of Pretoria, they are busy with, and also CSIR, they are busy with training, working on LLM for South Africa, using local languages. Okay, this is our potential users. We have DFFE, we have Daldorat, which is now department, the divided is agriculture and also land. Provincial governments, we have metros, mining, they can use this agent, agriculture, insurance, because the agent also has risk assessment, infrastructure, asset monitoring, they can also use it. And internationally, we can work with SADC members, development banks, NGOs, and others, UN agencies. So this is just, I just wanted to, the risk of adoption or risk of actually completing this project. Some of the risks, it can be, the main one is funding. So after demonstrating if, actually this is a pitch, it's kind of a pitch. So we need people to support us so that we can make sure that it's deployed everywhere. So we have a medium risk, which is funding, the first thing, and then another thing is market competition. Maybe people, they also started working on something like this. And yeah, things like, because some of the data we rely on, we use European and or other countries' data, geopolitics, they spoke about geopolitics this morning. So it's one of those where we might not get the data because of that. All right, it's the end of my presentation, but before I say thank you I just want to showcase it. Okay? So this is just a prototype. So this is a prototype. We have monitoring agents. So those monitoring agents, they use satellites. So we don't just use one satellite. We use all satellite MODIs, we use Landsat, we're going to even incorporate some of the data from SANSA archive. And we have, and also we use ground sensors, we use source weather and also other open source weather website from weather websites. And then we have a decision agent. That one is talk about the risks, so resources allocation. And then the other one is disaster management and communication, because communication is important. So communication agent is the one that is going to tell you if there's the alert. So I'm going to, I don't know if I'll be able to, okay. Go to deforestation. I don't know if, okay. So this is like when you press the deforestation, is the agent is going to run behind, and it shows where there's a kind of danger. Like if there's any deforestation, then it will tell you that there's a possibility of deforestation or there's a deforestation. You can zoom them, and also you can see the alert there. This alert is because of that communication agent. So it will tell you that there is something that is happening. You can see Devon, around Devon, no deforestation in that area. So I'm running it actually locally because I couldn't link it with the server. So most of the information will be like maybe a month or 3 months from 3 months ago. Just go to fire risks. So also you can even go to days, a number of days prediction there, and then it will show you. The fire one is based on those parameters. We have wind speed. It will also use historical risks, data, topography, and fuel moisture and biomass. So it incorporates all those variables. And then it will then say, okay, there's a possibility there, there's a danger, those colors there, it's the status. And then if you go to crop health. So currently crop health is based on, we know that in NDVI is an index, it's an indicator of crop health. So it's based on that. There are certain areas, they just say the green one, it means it's healthy, and then the red one, there's a farm there, it shows that there's something wrong there, but maybe around that area, because it's already like autumn, maybe they harvested. And then the orange one is when it's in between. And then go to, and you can also change the region, you can change we don't have other crop type. You can go to agent control. Agent control, just before deforestation. So agent control, here you can see this, if you wait a little bit, I don't know if, because it's locally, it's changing. So it's the warning, it's telling you the warning. So because it's the agent that is working 24/7. So it's working 24/7, and then it's predicting and giving you the information. You can link this with the WhatsApp, where people, they can get information, this information using on their phones. So these are the agents that are in here: communication, disaster management, alert, prioritization. They can even prioritize alert based on the severity. and we have also pattern recognition. So behind this, we have various models, mainly they are neural networks, and also pattern, and also deep learning models. And then we have localized models that we also incorporated. And then we're still going to add things like drought monitoring and also bush encroachment. Okay, I think I can stop here. Thank you.
Thank you very much, Dr. Masimula. And apologies, I have to stop you. We are running out of time. But if there is maybe one or two quick questions.
Hi,
Yes.
my name is Lesetja Moroba. I'm the chairperson of the Space Committee for Aerospace, Maritime and Defense Industry Association. I've got two questions. The first has to do with the data that's being sourced on the current presentation we saw from Cecilia. Do we have any sources from, say, China on the Beidou constellation that might serve as a redundancy? And from the ionosphere discussion, I'd like to find out if we're using any test equipment for quantum navigation, quantum dots and the like, to be able to circumvent some of those problems. Thanks.
Okay, thank you. No, we are not using, you are talking about data from China? No, we are not using any data because it's just a prototype. I'm still using Sentinel, MODIs, you know, those freely available ones. Yeah, I still need to incorporate others later.
Okay.
Actually from the same system that Mr. Sibeko presented.
Okay. Maybe you can repeat the second question.
The challenges related to GPS challenges when there's a solar storm. Is there any test bench currently around quantum navigation and Q dots to be able to circumvent that?
Okay. Yes.
Thank you for the very advanced question. Currently, no, we don't test that for now. But Mpuken, maybe she's the head of space.
I think, so what we do is with our GNSS data or receivers that we have, because we'll be receiving from all the constellation, the Chinese and the GLONASS and GPS. So the quantities that we are deriving from there is the total electron content that you have seen, and then the other one is scintillation. So it's like the signal phase, and so we just calculate the background, what the background is during quiet time, and then when there's a storm, we know how much is that storm deviation from the normal, but we don't do any further analysis from there. Yes, there's a question. Maybe you can stand up and try to speak up.
My problem is that I said I was pitching, so now. Yeah, but let's say for mining, we can, they can use this system to alert them when there's the illegal mining, even though it's not yet incorporated here, but it's something that we can have a business in terms of we develop this and then for legal mining. Yeah, and even in banking, there are a lot of things like fire, they can monitor that with fire insurance as well. I mean, in terms of insurance, they can even use it to actually to prove that there was a fire somewhere. Let's say they receive a claim, those kind of things.
Thank you very much for the question. I think the big thing is just getting it out there that South Africa has got a space organization. You know, I think getting it out there to the normal public, the response we've had on our media platforms, you know, whether it be the interview that we had with the ladies, with the forecasters or that, you know, a lot of people don't know this. And when it comes to even drone operators using it for the movie industry, guys using drones for agriculture, you do a mapping of spraying or anything like that, or in the mining industry, or our port at Kucha, where we've done mapping with drones, something like this could be disastrous, you know. So if you can introduce them to space forecasting and let them promote it in their industry, I think it'll be incredible. I think, you know, space is endless. So yeah, just word of mouth and talk about it. Let people know about it.
Thank you. Okay, thank you very much. I see there are more hands. Okay.
Thank you. Right, Tongwane Namane, Commercial Director at SES Space, as well as Vice Chairperson for the Aerospace, Maritime and Defense Space Committee. My question is directed at Dr. Masemola. Thank you so much for bringing this to the fore. I think it's quite exciting that we're using, you know, AI in doing data analysis on our space data. All right, I have 3 questions, and they're a little bit technical, and it's based on intellectual property, cybersecurity, as well as the application space. So, I mean, this is like edging towards what we're looking at, the holy grail in terms of in-orbit onboard computing for satellites, the capability to have threat detection and utilize autonomy when it comes to AI. So what level would you say that the autonomy is, firstly? Secondly, since we're utilizing data that is being basically put out by European systems as well as American systems like Landsat and RadarSat and, you know, Copernicus, what type of effect will that have once we start developing the intellectual property that is solutions focused, particularly for South Africa, but also we develop then IP for systems that are able to utilize, you know, agentic AI and general AI to be able to do a data analysis, let's say for national security applications. What would we do in that case? And my last aspect in terms of cybersecurity is, I really like the fact that you were mentioning that it's been run on localized system, but we do know ultimately that will it be tied to the net? Who will have access to this? How will the data be ring-fenced? How is it protected? And who is it protected by? Because the question around data sovereignty is very important. It doesn't really matter what the data is, but what's absolutely critical is how the data is processed and for what purpose. Once again, I'm going to bring in national security interests. So where does the line lie ultimately by making sure that, you know, we have back propagation as well as testing systems to ensure that the AI is giving us accurate information in terms of threat detection, but also making sure that we're protecting that information within, you know, the Republic of South Africa, and if we want to, from an intellectual proprietary perspective, bring that out into the SADC region, continentally as well as globally. Thank you.
That was loaded. I think it's your question, because I didn't really hear your questions because it was like, I think you are talking about protection of data, right? And also protection. Oh, okay. Oh, okay. Intellectual property and as well as cyber security. Some of the questions I will ask, I will answer after this. I'm not going to answer here. But in terms of cyber, yeah, this one is, that is why I always work like locally. Like I don't, like even to feed data on online, what do you call, softwares or all this AI. I work locally, and then before you deploy, and then you work with cyber. I'm not a cyber security expert, and then we work with cyber security. From example, I did something like it was on precision agriculture where I was before, and then we worked with cyber security people to actually to make sure that everything is protected. And in terms of IP, you know that when it comes to software technologies, yes, we, yeah, IP, how you protect it, I think you just have to work with people who knows about all this IP, how to protect, and then you get advice from them to say how we can actually protect our IP. But in terms of security, I think cyber security people will answer that. Right now, I work like locally, and then before I can deploy anything somewhere, and then I have to talk to cyber security people because they're there to actually to protect us researchers and people who develop and to say, okay, before you take it outside, let's do this and this and this and this.
Okay, thank you very much. I will not take any further questions because we are running out of time. So just a takeaway from this session, the showcasing session, is that you have seen the Earth observation team presenting the space-based solutions. And then as we develop these national space capabilities, we need to ensure that we protect our space-based technological systems from the impact of space weather. And then we have a space weather forecasting team who are working in Hermanas, and they are monitoring the space environment. So it's important for us to be aware that as we launch our satellites, there is also a space environment. Thank you very much. Let's thank our speakers. There is now welcome reception at the deck. So I think we are done for today. Thank you very much.